So we were saying that in the first case, if we have gamma fluid larger than gamma body, to reach equilibrium state, we should have floating conditions. Okay? Now, going back to our expression, the weight is gamma of the body times the total volume, V total. And the buoyancy force, F buoyancy, is equal to gamma of the fluid times V submerged. Okay? If, so this is, for this condition, we have floating. Now, for the other case, if gamma fluid smaller than gamma body, what will happen? Even if we increase the submerged volume to the maximum, what is the maximum value of the submerged volume?
Total volume.
The total volume, exactly. Because as the body will move downward, the submerged volume will increase. And when it is totally in the fluid, then the submerged volume is equal to the total volume. So since the maximum possible value is V total, okay? And we have that buoyancy force is gamma fluid times V. So the maximum possible buoyancy is gamma fluid times V total. However, for the weight, it's gamma body times V total. So this term will always be larger than the buoyancy force because gamma of the body is larger than gamma of the fluid. So in case gamma fluid is smaller than gamma of the body, then the body will continue to move downward because the weight will overcome the buoyancy force. It will continue to move downward until reaching a certain ground level. And the third possible case is that if exactly gamma fluid equals to gamma body, in this case, if we just put the body somewhere within the fluid, it will remain at its place because the buoyancy force and the weight will just cancel out. Okay? So these are the main three possibilities that we have. Now, how we can demonstrate that the buoyancy force is equivalent to the weight of the displaced volume? Again, same concept, okay? So here, for example, in the following slide, let us consider a certain small element of interest, okay? So if you go to a certain body, sorry, 1 second. Okay. So we have the following body here. And we are interested into calculating the expression of the buoyancy force. If I want to derive the expression of the buoyancy force, I take this control volume, okay? And I do the balance of forces. So again, here along horizontal direction, effects will cancel out because we have seen that pressure forces of the liquid, which will be transmitted to this element, are equal in a horizontal plane. So no resultant force along the horizontal. I will just have vertical forces, okay? Now, this element is subjected to which forces in the vertical direction? First, of course, its own weight, okay? So its own weight, which is acting downward, so W. It's also subjected to pressure forces at the upper level here. So it's P. If we can, P1, let's call it. If this is surface 1, this is surface 2. So the force here is P1 times dA, okay? While if I take the bottom here, the force is upward because always the force of a fluid on an object is perpendicular to from the fluid towards the object. So this is P2 dA. Now, let us write what are the expressions of P1 and P2. I know the pressure at level P0. So if I am at a certain depth H1, P1 can be replaced by P0 plus gamma or rho G H1. So plus gamma H1. And of course, I multiply by dA. So this is your, and since it's a downward force, when I take it into account in the balance, I put minus P1 dA. So this is the force from the bottom. Sorry, from the top. Now, if I consider the force from the bottom, it's P2 times dA. Now, if I want to express P2, it's P0 plus the action of the fluid column, which is gamma H2. And I don't forget, of course, to get the force to multiply by dA. And since it's an upward force, I will put it as plus P0 plus rho GH2 times dA. So this term represents the component from the from pressure from the bottom level. These two, okay, I should subtract from these two the weight of the body I am considering. This is the body I am considering here. Okay. And if you take, this is equal to 0. If you take weight of the body to the other side, you will get the following, that P0 plus rho GH1 times dA. So this is, as we said, this is P2 minus P1 times dA equals to the weight. Okay, so this is the weight W of this part. Okay. Okay. So this should be equal to W of the body. What is W of the body? W of the body is equal to gamma of the body times the volume, okay, times the volume, which is dA times H2 minus H1. Of course, what I am writing is applicable in equilibrium conditions. Imagine that I don't know if I have equilibrium or not. I want to compute only the buoyancy force and then compare it to the weight. What is the buoyancy force then? The buoyancy force is the net action of the fluid on my control volume. So it's due to the summation of this effect minus this one. So here, if you take into common dA, and also, as you will see, P0 will cancel out because it will appear in both terms. If I take into common dA and rho g, what do I get? I get that this buoyancy force, this is the action, it represents the action of the fluid on my control volume. So this is the action of, this is the definition of buoyancy, action of fluid on a submerged body, okay, or on an immersed body. Okay, it's equal to what? It's equal to rho g times H2 minus H1 times dA. Let us try to do an interpretation of this term, a physical interpretation of this term. The physical interpretation of this term is rho g represents gamma, and delta H, H2 minus H1 is this height. If you multiply this height by dA, what do you get? You get this weight, sorry, this volume, okay? The volume of concern. So this is, you can replace it by the immersed volume, V immersed. But since you are multiplying the immersed volume by gamma of the fluid, not gamma of the body, then your buoyancy force is equivalent to what? Is equivalent to the weight of the displaced volume of fluid. So we call this volume because the body, this volume of the body have taken a certain volume, has taken the place of a certain volume of the fluid. So this is why we call it, it's the replaced volume, okay, or displaced volume. So this is the displaced volume, but since I'm multiplying this displaced volume of fluid by gamma of fluid, so it will not represent the weight of this part of the body. It will represent the weight of the fluid for the same volume, okay, which is called the displaced volume of fluid. I just multiply, when I multiply V displaced by gamma of fluid, I will obtain the corresponding weight of fluid if it is filling this part, okay, which is the part replaced by the body, because the body will replace a certain volume of the fluid. It will occupy a certain volume. So this is why we say here this volume is called displaced volume of fluid. Okay, so we deduce now from this analysis that buoyancy force is nothing than the weight of the displaced volume of fluid. Okay, and now to know if we have equilibrium or not, if we have equilibrium conditions, then we can deduce that this buoyancy force should be in equilibrium with the weight of the body. So when it is in equilibrium with the weight of the body, okay, if gamma of both are equal, then the volume submerged will be equal to the total volume of the body. In case gamma fluid is larger than gamma body, I will have a floating condition until reaching V immersed times gamma fluid equals to weight of the total body. And finally, if gamma of the fluid is smaller than gamma body, the body will keep moving down until reaching a certain ground. Okay. Any question on buoyancy? Let me check the chat. Oh. It's very important. Buoyancy is very important, in what? In design of boats. Because you know that for a boat, I cannot allow to have complete immersed body. So I should always have floating conditions. And for example, in the case of Titanic, there was a certain problem in the design, which led to the catastrophic event we know. Okay, so in general, how we do the analysis and how we try to design our shapes. This is a small example to tell you that I can do a proper design in a way to always have equilibrium floating conditions. Okay, let us consider this symmetrical shape, and you have this axis of symmetry. If it is just in the symmetrical position, then it will be always stable. Why? Because here, if you do the analysis, okay, you have that already buoyancy force and the weight are acting along the same line. So they don't have any possibility to produce a moment. You know that for equilibrium conditions of rigid bodies, I don't care only for sum of forces equals 0. So even if sum of forces equals 0, I still have a second condition that sum of moments also is 0. So if my structure is to be stable, I should always be able to get sum of moments about G equal to 0. When it is just in this straight position, this is satisfied because both the buoyancy force and the weight will pass by G, so I don't have any problem. Now consider that you know that, of course, during a trip, the boat can have some disturbances. What I should do is that whatever is the disturbance, I should locate my buoyancy point should always be in a way to give me a restoring moment. What do we mean by restoring moment? If you look at the following figure, if you do a small disturbance angle, of course, the immersed volume will change. Okay, and since the immersed volume will change, the buoyancy force also will change in magnitude and in position. And I have to add something. We have determined the magnitude of the buoyancy force. What is the point of application of the buoyancy force? The buoyancy force should always pass by the centroid of the submerged volume. Okay, not of the center of gravity of the whole body. No, it should pass by the center of gravity of the submerged part. Okay, so here, if you look at this figure, when you have a small tilt, the area that is submerged or the volume that is submerged will be different. Therefore, also the buoyancy magnitude and its location will be different. And now, if I draw the buoyancy force and the weight, I will have a certain, by doing this tilt, the buoyancy force will have now a moment about G. But what is good in this example is that the moment of buoyancy force about G is clockwise, which is opposing the tendency of disturbance. So here the disturbance is counterclockwise. The buoyancy force is causing a clockwise moment. This is why we call it restoring moment. This moment here will tend to go back to the equilibrium position. This is why when we design boats, we make sure that for any tilt angle, always the buoyancy force will give me a restoring moment. If I don't have this, I might have a risk of, I will have no floating condition maintained, and it's a disaster. Okay, so the second possibility here, for the same shape, if I increase a lot the disturbance angle, now it's not a good case for me because the buoyancy force will change location, and now it will do an overturning moment. So this is why this shape is not recommended for boats, because if I use them in this shape, if I have a high angle disturbance angle, the buoyancy force will do an overturning moment, and this is failure. Okay, this is why if you look at the figure, to be able to ensure a good design, always the intersection point. So here, if you have the line of symmetry passing by G, and you have the line of action of buoyancy force, when the intersection point between these two is above G, you have stable conditions because the moment will be a restoring moment. While if you look at the axis passing by G and the line of action of F, if their intersection is below G, then you have a problem. This is why when we design the shape, we try to say that whatever is the position, this intersection point should always be above G. So this is how we design the shape of our boats. Okay, in a way to avoid any overturning moment, because it will, as we said, it will prevent maintaining floating conditions that are safe. Okay, so this is about buoyancy. Let us do a problem to practice on buoyancy. So if you go back to the problems, we have in the following problem, the uniform beam in the figure is of size L by H by B, with B and H much smaller than F. A uniform heavy sphere tied to the left corner causes the beam to float exactly on its diagonal. We want to show that for this condition, the relation between gamma of the body and gamma of the fluid is that gamma body is gamma of the fluid over 3. And also, we need to verify that the diameter of the sphere should satisfy the following relation. Okay, so first, why we are in a buoyancy, just let me check your chat before starting the problem. Ihab, as I told you, the buoyancy force should always pass by the center of gravity of the immersed body, okay? Like the weight is passing by the center of gravity of the whole body, the buoyancy force is passing by the center of gravity of just the immersed body, okay? So if I look at the following figure, I have a certain shape, okay, and it is floating in equilibrium conditions. So I have floating conditions. So first, I want to demonstrate that to have this equilibrium condition, I should have the following relation between gamma of the body and gamma of the fluid. Let us try to think together what is happening here. First, in any problem like this, start always by saying what are the forces acting on my system. Okay, first, my system of interest is this one, and we have several forces acting on it. First, we have the weight of the body, WB. We have the buoyancy force, okay, and as we said, the buoyancy force should pass by the centroid of the volume. So if I'm considering this is the volume immersed here, the buoyancy force should pass by the centroid. And we know that for a triangle, we know how to find the centroid. It's the median, it's intersection of medians. Okay, so you have a triangle. If I take two medians, the intersection of these medians will give me the location of the centroid. So it's nearly here. And another way to find it, we know that it should be at 1/3 of the height from this level. So what we will do now, this is the buoyancy force point of application. So this is F buoyancy. But here we have something else. The additional force is the tension force here. So we have also T. As you can see here, we want to demonstrate the following relation between gamma body and gamma fluid. And in this relation, the tension is not appearing. How do you think I can cancel the effect of tension? By using which equation? If I use sum of forces equals 0, it will not work because I will have minus tension, minus weight of the body, plus buoyancy force equal to 0. So since I want to eliminate the tension, what do you do in statics? Very good. You take the moment about C. Okay. If you remember, when I do sum of moments in equilibrium condition, if I do sum of moments about any point, it will give me 0. And since the tension is passing by C, then its moment about C will be 0. So when I write sum of moments about C equals to 0, I will just have the moment of the buoyancy force and the moment of the weight force. Now let us take a small look at our figure. First, they told me that the length L here, okay, is much small, is much larger than the thickness here, okay, the height here. So this means that, okay, if I draw the following line, this line and the median line here are nearly, if you want, collinear, because this angle is very, very small. It's nearly 0. This means what? This means that since I know that this angle is very small, okay, so I can consider so this angle is nearly 0, okay. Then this length here is nearly equal to the length of the diagonal. So what can I deduce then? I can deduce that the point of application of the buoyancy force is nearly at L over C from point C, okay? Because when this angle is very, very small and these two sides are nearly equal, okay? So this angle will be an angle of, I will have 90 degrees here. So it's like this is the height of my triangle. And we know that the point, the centroid, is at 1/3 from the base. So this distance can be approximated because h is much smaller than L. This distance can be approximated as L over 3. So when I represent the buoyancy force here passing by the centroid, its line of action is at a distance of L over 3 from point C. So now, if I want to represent the moment of this force, let us select a positive convention. If I consider that a positive moment is clockwise, so if I consider the clockwise moment as positive, then the buoyancy force is producing a negative moment because this buoyancy force is tending to rotate counterclockwise about C. Okay, and you know that to get the moment, what do? You multiply the distance, which is here L over 3. So this is L over 3 times the magnitude of the buoyancy force FB. Now, what is the magnitude of FB? We said that the magnitude of the buoyancy force is equivalent to the weight of the displaced volume of fluid, since which is equivalent to the immersed volume of the body. This is the immersed volume. It's equal to the volume of this triangle. And as we said, this triangle is nearly a right triangle here. So what we can do, we can just do base times height over 2. And our height is nearly equal to L because, as I told you, the angle here is very small. So I can say that my height, so this is L, the base is H, so this volume here is L times H times the width. They told me that the width is B, so times B over 2. And here, even if H is not smaller than L, this will remain valid. Okay, this will remain valid even for large values of H because this is a rectangle. Okay, so this is the volume LH times B over 2. I multiply it by gamma of the fluid. I get what? I get the buoyancy force. And then, so this is my immersed volume multiplied by gamma fluid will give me buoyancy force. And then multiplied by the distance to C, which is L over 3, I get then the moment of the buoyancy force about C. Now, what is the second force producing a moment about C? It's the weight. And the weight is acting at just the center of gravity of my system. So it's passing by the center of it's at the middle of the diagonal. This is the weight. And here, as we said, the diagonal is nearly equal in length to L because H is very small. So this distance from this point to this one is L over 2. And since the weight is tending to cause a clockwise moment about C, and I consider the positive convention to be clockwise, so I should add plus the weight, which is equal to gamma of the body times its volume. The total volume here I will consider because this is my whole body. The volume of the body VB is equal to H times L times the width B. Okay, so now after I get the volume of the body, since I want the weight of the body, I should multiply by gamma of the body. So this term here will give me the weight, WB. And finally, I should multiply by the distance to C, which is L over 2. When multiplying by L over 2, I get the moment of the weight of the body with respect to C. And since I am working in equilibrium conditions, sum of moment should be 0. If you compare terms, LHB here will cancel out, LHB. You have LL and over 2. What will remain is that gamma of the body should be equal to gamma over 3. And you can verify that since here what is happening, you have that gamma of your body is smaller than gamma of your fluid. It's 1/3 gamma of your fluid. Okay, and this is what we wanted to prove here. Okay, now next step, they want us to demonstrate that the diameter of the following sphere should be related to dimensions L, H, and B, and the specific gravity of the sphere by the following relation. How we can think in such questions? How to start? First, you need an information about the sphere. Since you need an information about the sphere, the first step you can do is to take the free body diagram of the sphere. If you consider the free body diagram of the sphere, what are the forces acting on it? You have its own weight, W sphere, and what also? You have the tension T, okay? And since it's a cable, so you know that the cable will transmit the tension everywhere in its point. So in any point here, I will get the same tension T. So I can say that this tension T is equal to the one acting at C, TC. Okay? So here, if you want, it's a little bit a static question. Okay. So if I consider, did I miss something here in the free body diagram of the sphere? What should I add in addition to T and to the weight of the sphere? Who will tell me? Very good. Buoyancy on the sphere. So I missed one force, which is F of buoyancy on the sphere. Okay. Now I am ready to write my equilibrium relation for the sphere. So first, I will say that for my sphere, if I write the equilibrium relation for my sphere, I get the following. I have plus tension T minus the weight of my sphere plus F buoyancy on the sphere equals to 0. So this will give me that the tension T is equal to the weight of the sphere minus the buoyancy force on the sphere. Now, since my sphere is completely immersed into the fluid, okay, then of course the weight of the sphere is gamma of the sphere times the volume of the sphere, while for the buoyancy force, also since it's completely submerged, I will take the same volume, but of course gamma of the fluid. So I will replace F buoyancy by gamma fluid, which is gamma times volume of the sphere. So let us take the volume of the sphere into factor. What do we get? We get then that the tension T is equal to the volume of the sphere times the weight, times gamma of the body, okay, of the sphere, if you want, we'll call it now, gamma of the sphere minus gamma of the fluid. Now look, what they asked for is to include the specific gravity. So let us remember together what is specific gravity. Specific gravity of a body is the density rho of the body. So here it's rho of sphere over rho of water. Okay. Here, since the fluid is water, so they should mention this for you. This is water. Okay. Since the fluid is water, now since I know gamma, I don't know rho. What I can do, since G is a constant, if I multiply by G the numerator and the denominator, nothing will change. And I can replace then the ratio of densities by the ratio of gamma. So I can replace rho sphere times G by gamma of the sphere. And I can replace rho water times G by gamma of water. Okay, which is here symbolized by gamma. So now, what can you deduce? If I take into factor gamma here outside, I will get that the tension T is equal to volume of the sphere times gamma. I will take it into factor to appear the ratio because I need to appear the specific gravity term. So factor gamma sphere over gamma minus 1. Now gamma sphere over gamma, I will replace it by what? This is specific gravity term. Okay. Volume of the sphere, you know that for a sphere, knowing its diameter, you can determine its volume. The volume of the sphere is pi over 6d cubed. So now we deduce that by doing the analysis on the sphere, the tension can be written as specific gravity minus 1 times gamma times pi over 6d cubed, which is the volume of the sphere. Now, to get our final relation, we need to equate this formula of T with another expression of T, since the tension acting on the sphere is equivalent to the tension acting on the body here. So what the next step, since I want to relate, look, how I know that I should do this, because we want to relate the diameter with the parameters of this body, LH and B. So we should, to connect these two, we should use the tension. The same tension here and here because it's the same cable. We got the expression of T by doing the analysis of the sphere. Now we will get the tension T by doing the analysis of this body, of the beam. Okay, so for the beam, now to appear T, I should do sum of forces along the vertical. So if I do sum of forces along the vertical, what do I have? I have the weight, I have the buoyancy force that is off, and I have the tension. So already we found together the expression of the buoyancy force. So this is F buoyancy on the beam. Okay. This is the weight of the beam, and this is tension T. So now, since we derived in the previous question that gamma of the beam is related to gamma by gamma beam equal gamma over 3, we can directly replace it here by its value. And then we get the expression of T just function of gamma, L, B, and H. And now we are ready to equate these two expressions. When we equate these two expressions, we just have to find what is D, and this is the question. We should find D function of L, H, B, and the specific gravity. So when you equate these two relations, you will get the following: gamma times L times B times H over 6 is equal to specific gravity minus 1 times gamma times pi over 6 d cubed. So first, you have a lot of factors that can be simplified. You have over 6 over 6. You have gamma and gamma. So now, if you take this term pi times specific gravity minus 1 to the other side, and since you have a cube here, you should do to the power 1 over 3. You will get that D is LHB over pi times specific gravity minus 1 to the power 1 over 6. Okay. Any question on this problem? Yes, Michelle, I will answer your question just to make sure you don't have any question on this part. So no questions on this part? Yes, Michelle, ask your question.
Doctor, can you please put the exercise we did last time about the curved surface?
It's posted.
Yes, but I just want to ask you a question about.
Oh, now you mean yes, of course.